Hello, my name is Eduardo Pavés, and I will be presenting our paper, Multi-Resolution Intra-Predictive Coding of 3D Point Cloud Attributes. This is joint work with Andrés Souto and Ricardo de Quiroz at the University of Brasilia and Antonio Ortega at the University of Southern California. I will start by introducing compression of 3D point clouds. Then I will introduce the regional adaptive graph Fourier transform, which is the main transform used in this work. Then I will go over how to do intra-prediction for multi-resolution transforms. I will then go into more details regarding how to construct these predictors using graphs. I will end up with compression results and conclusion. So 3D point clouds have become the preferred representation for 3D objects and people, outdoor scenes, and historical artifacts. This is because several applications where these point clouds are required have emerged, in particular immersive communications. These applications have become more prominent because the capture technology has advanced so that acquisition is cheap. It can be done at large scale and high resolution, and also in real time. This has motivated in the past few years some research in compression of this type of data. More precisely, a 3D point cloud consists of a list of points in 3D. Each of these points is represented by its X, Y, Z coordinates, and this sort of is used to represent the shape of an object. Points also have attributes, for example, color. So this work is about compression of point cloud attributes using the multi-resolution regional adaptive graph Fourier transform. Predictive coding is what I'm going to talk about next. So in traditional transform coding, you take a signal, you apply a transform, then you can do quantization and then entropy coding. In predictive coding, you have an approximation of your signal that we call X tilde. And then what you do instead of transforming X, you transform the prediction error or the residual delta. And then you apply a traditional transform coding approach on this residual. And if your prediction is good enough, then it has been shown that you can obtain very large gains. In practice, there are two types of predictive coding. One of them is temporal coding or interframe coding. And in this case, the approximation is obtained from a previously decoded frame. Another approach is intraframe coding, in which the pixels in the current frame or voxels in the current frame are predicted from previously decoded voxels, but in the same frame. So in video and in particular in point clouds, previous works on intra-predictive coding have used block-based prediction and at a single resolution. And one of the challenges for 3D point clouds is that the best transforms available are usually multi-resolution, so therefore intra-prediction has to take this into consideration. In this work, we use the regional adaptive graph Fourier transform. This transform can be described as follows. It takes a point cloud and partitions it in different blocks. At each block, it applies a graph transform. This transform produces one low-pass coefficient per block and several high-pass coefficients. All the low-pass coefficients are gathered, as well as the high-pass coefficients. Then this process can be repeated again on the low-pass coefficients. The full regional adaptive graph Fourier transform applies this process several times. And at each resolution level, it's working on a point cloud represented by VL with attributes AL. This whole one-level process can be described as a simple linear operator that takes the attributes at a given resolution and produces approximation coefficients at a lower resolution and detailed coefficients. The RAGFT is usually incorporated into a transform coding framework for completion of point cloud attributes. It's also known that this transform is orthogonal. It has the constant DC property, and it has like a scalable complexity. In terms of coding performance, it cannot perform the RAT, and by significant amounts. However, the coefficients at different resolutions are still correlated. So what we do in this work is we exploit this correlation to improve the coding performance of the RAGFT. Now I will introduce multi-resolution intra-predictive coding. The goal is to predict the detailed coefficients at resolution L from the coded approximation coefficients at the same resolution. First, we apply the forward RAGFT and collect all coefficients and all resolutions. Second, we encode the approximation and detailed coefficients at the lowest resolution. Then the decoded coefficients are passed through the inverse RAGFT for this level to obtain decoded approximation coefficients at a higher resolution. Now, for a given resolution L, we have two inputs: the signal that we want to encode, the detailed coefficients, and the previously decoded approximation coefficients. We use these approximation coefficients to predict the detailed coefficients. Then we compute the difference between this estimator and the detailed coefficients, and then pass them through a traditional transform coding system. In the decoder side, the delta coefficients are decoded and then are used to reconstruct decoded detailed coefficients. These are then combined with the approximation coefficients to produce an approximation coefficient vector at a higher resolution. This intra-predictive coding approach can be implemented recursively at this high resolution now. An approach of this type has been proposed for the RAT, and it has been adopted by MPEG. The goal of this work is to introduce a prediction method when the transform is the RAGFT. To do this, we need to introduce some concepts about graph signal processing for 3D point clouds. A graph is a set of nodes. In this case, nodes represent points in a 3D point cloud. Edges are connections between these nodes, and we consider weights that are inversely proportional to the distance between the points. A graph signal is a function of the nodes of the graph. In this case, we consider the point cloud attribute as the graph signal. Now recall that the goal is to predict the detailed coefficients from the approximation coefficients. Our approach goes as follows. We take the approximation coefficients at a given resolution and then replace the detailed coefficients by zeros. We apply one level inverse RAGFT, and then we obtain a piecewise constant signal. This signal is then low passed using a graph filter, resulting in a smoothed signal. Then we apply one level RAGFT, which produces an approximation of the detailed coefficients. This d tilde is used as our predictor. Note that in practice, we need to add this additional normalization step. You can see the paper for details. In GPCC, there is a method for constructing predictors for the RAT. What they do is, let's say, for this red point, a predictor is constructed based on nearby points in the lower resolution. What we do here is we first interpolate the point cloud from low resolution to high resolution, and then the predictor of the red point here is a linear combination of the nearby points instead of the nearby blocks. Now I will go and show some results. We consider several methods. First, we consider the RAGFT, and we consider two cases, the one with large block size, which provides the best results for this method, and the one with the smallest block size, or block size equals 2, which has a performance comparable to the RAT. We also implement our intra-predictive RAT based on the GPCC code. take these coefficients. We also implement a prediction method for the RAGFT that is similar to what is done for RAT based on the low resolution point cloud. We also implement the proposed intra-prediction method. And for all these methods, we use uniform quantization and independently entropy code them. On the right, you can see results for one frame of the LUT sequence. Overall, we observed that endowing the RAGFT with intra-prediction achieves gains from 1 to 2 dBs, even if the intra-prediction uses the lower resolution point cloud. By using the improved filtering approach in the high resolution point cloud, we can get gains of another dB. Most importantly, the proposed intra-predictive RAGFT outperforms the intra-predictive RAT at all bit rates by up to half of a decibel. We also compare the reconstructed decoded signals at a constant bit rate. On the right, you see the RAGFT with largest block size. As you can see, this reconstruction has very obvious blocking artifacts. The intra-predictive RAT, it doesn't have these blocking artifacts, and it provides a much better reconstruction with also a gain of about 0.9 dB with respect to the RAGFT. Finally, the proposed intra-predictive RAGFT improves over intra-RAT by about 0.3 dB, but more importantly, it preserves better the details. In conclusion, we proposed a multi-resolution intra-prediction strategy for the regional adaptive graph Fourier transform. With this method, we improve over the intra-predicted RAT. This is because the proposed predictor exploits higher resolution geometry, resulting in these improvements. And also the complexity of the proposed approach is comparable to the complexity of the intra-RAT. Thank you. If you want to see more details, please look at our paper, which is available online. I will be happy to answer any questions.